have to put in where, in essence, where are you putting the leads? If I'm measuring equivalent capacitance, I should be able to take a multimeter, which measures capacitance, and put them somewhere. Now I'm gonna get a different answer depending upon where I put it. So generally, you just stick something out at the end to indicate that's where I'm putting it. There was a test question where I can't remember if I did it with capacitors or resistors, but I basically set up a situation like this. Gave you the value of the capacitors and marked that as point A, B, C, and D. And the question is, where do you put the leads in order to get the maximum capacitance? Where do you put the leads to get the minimum capacitance? And it does matter where you know, which two corners you put them on. Okay, oh, I need numbers here. 1 farad, 2 farads, 3 farads, 4 farads, 5 farads, and 6 farads. What do we do first?
Circle the junctions.
Say it again.
Circle the junctions.
All right, got a junction here, a junction here, a junction here. So, I know that this is parallel with that. And that is parallel, actually that's one giant junction right there. And this whole thing is parallel with that.
Can we start with the 2 and the 3?
Absolutely. I can't start with the 2 and the 4 because they aren't in parallel by themselves and they're not in series. So I have to start with the things that I can do. 2 and 3 are together, they're in series. So I got 1/2 plus 1/3 is 5/6. So my equivalent capacitance, 1.2 farads. So I've now broken this down into, I've got a 1 farad right here, and then it splits. Actually, it splits 3 ways. I've got a 1.2 farad this way, I got a 4 farad this way, and I've got a 5 farad down this way.
Why don't you just add all those up? The 1.2, 4, and 5?
Yep. If you didn't recognize, because the way I drew this, you didn't recognize that all 3 are in parallel, then you could just do 2 of them and then say, oh, that's in parallel with this one, and then add the other one to it. It does not affect the final results, so that's 10.2. So now I've got a 1 farad, 10.2 farad, and a 6 farad. Series, so we're doing reciprocals. 1/1 plus 1/10.2 plus 1/6.
You should have left it as 6/5. Then it would have been easier, because you would have had 5/6.
I still was gonna add to the other ones though. So that would be, so 10.2 is 51/5. Yeah, so I'd have a 51 down there in the denominator.
Yeah.
To me, easier would be plugging it into a calculator, but for you fraction fans, go for it. So whatever C you do.
I got it.
Okay.
Well, it is that, but then you have to 1 divided by it, so I got 0.79. Is that right?
Yep.
Okay. Farads.
Thank you.
Sorry.
What is the EQ on the capacity?
EQ for equivalent. It's equivalent capacitance. Oh, did I miss your question?
What is it, what do you mean by equivalent?
In other words, the equivalent capacitance, what I'm asking for that is, if I took all of these out, what would be the capacitance of one capacitor that is a substitute for all of this?
Oh, okay, and then it would be 0.79.
Yeah.
Okay.
But isn't there a reason usually why you have a ton of different capacitors put together? Instead of
Why
just
you
one?
would?
Yeah.
From a design point of view, probably not gonna happen, but the scenarios I picture where it's happening is if there is a change in specs, and, you know, I could take out a capacitor and then replace it, or I could just add a capacitor.
Mm-hmm.
And so that's the case where it happens like that.
Because I always found it kind of weird, like especially when you have it in series, because then you end up lowering the capacitance, and unless you want a lower capacitor, it seems kind of counterintuitive.
If you're making a taser and you put in some value and then suddenly you realize, whoa, that can kill somebody, we need to lower the amount of charge that we're storing,
Mm-hmm.
that would be a situation where you'd want the lower capacitance.
But then why not just put a smaller one?
Why not what?
Why not just put a smaller capacitor?
And maybe that's what you come up with.
Are they more expensive? Like, is there a...
Depends on the purpose. The capacitors that we buy here, cheap.
Oh, okay.
We don't have grade A capacitors.
Yeah, we're not trying to disable anybody or, yeah, we're not trying to disable anybody.
No, I was just kind of curious about like the application.
Mainly, what I'm going over here is a thought process.
Oh, okay.
I like this, I actually understand.
Test 1B typically is a much better experience for people than any of the other tests.
We have 4.
Yeah, including the multiple choice. All right, questions to hear? Well, it's in the master set, so I'm not gonna do one of those here. All right. The one where I give you the capacitors with a variable capacitor and say I want total equivalent capacitance to be within a certain range, and then you have to sort of design what it is. Not right now. I've talked about current, so let's talk a little bit about current. Current, as I've written before, but I will write again officially. Capital I. More specifically, that's a DC current. All the charges will flow in the same direction. When we get to AC current, which shows up in a couple weeks, 8, so this would be DC current. AC current is represented by a lowercase I. So current is just basically, I've got a wire here, I have charges passing by it, and so the charge that passes by within a certain amount of time, that's my current. We can write as dq dt if we have a fluctuating current. Now from a classical physics point of view, a wire has some thickness here. So I've got some wire. And as an electron starts flowing through it, it doesn't just travels straight through it, and it's not like it's an empty pipe, and under normal circumstances, it's gonna hit something and then bounce, and then hit something else, and then bounce, and hit something else and bounce.
Is there a reason why the ends look like that?
When I was taking engineering classes, this is the way that the professors drew it to indicate that this is just a small part of it.
It's like a cross section, kind of.
Yeah. Trying to get some depth to the wire. Now, the speed with which the electron actually travels, generally indicated V sub D for drift speed.
Yeah.
So when I talked before, even though the current will be, I connect a wire to a battery, it is almost immediate, actually in terms of microseconds. I had a truck with a battery was, sorry?
What is the subscript on B?
D as in dog, or drift. It's not venereal disease. Which I think is an archaic term at this point.
I don't know what it is.
You don't know what a venereal disease is? STI?
You don't want one.
Oh,
I think they're called STIs now.
or STDs.
Yeah.
Oh. Okay. Why can't the language just stay the same as it was in the 60s? Hey man, you know, it's all cool. All right, so drift speed, because the drift speeds are usually in the order of centimeters per second. But the current is almost immediate. Sort of the example I started on, say a truck where the battery was not tied down properly, and it tipped over as I was going around a curve. The two leads touched the side of the truck and discharged immediately. Killed the battery right then and there. It was immediate. So
Sweet.
fortunately, I was within walking distance of home. But the actual speed of the electrons are small, but the current, because in order for this to move, that means that another electron has moved, and you basically have these holes that are, the electrons all sort of move en masse.
How did it just fell?
It tipped over.
What kind of concerns? My truck doesn't have a battery tray. So now you're concerned me then.
Who gets your bungee strap?
It could be that you're in for a physics lesson as you go around a curve.
I have two batteries though, so maybe, what would happen then?
I assume when one discharges, the other one picks up, or is it that they're both at the same time, used at the same time?
I think it's only both used to start it, though.
Okay. So just never stop your truck.
Or I'll just keep it running forever.
That sounds like a good environmental plan. Now, in order for the electron to drift, there has to be some voltage attached to it. So, you know, I might have a positive side, you know, this might be connected to a battery. But from a different point of view, I have an electric field here. Electric field goes from positive to negative. I have an electric field that's in that direction, going from the positive to the negative side. So this electron has a force on it that's causing it to move in this direction. And the force on the electron is just, is Q times the electric field. I'll keep generic Q for right now, I'll change that at some point. I know that's equal to mass times acceleration. Not worried about gravitational forces here. Now, the acceleration of it, it's going to hit, basically stop and then move, hit something else, stop, move. It's going to constantly be hitting and moving. And so my acceleration, I can just treat as velocity over time. And the amount of time it takes to go is Suddenly blanking on the term. Mean path time? Thanks. No, labeled it as tau. It's basically, it's the average time between hitting items. Mean free path time. It's the average time that it's actually not hitting anything, in other words, the average time it's in a free path.
Sorry, is that an equal sign between the V over T's, or is that a multiplication?
That's an equal sign there, equal sign there.
Thank you.
Yeah, and I did a hand wave here, let's just, if acceleration is constant, which is reasonable-ish. This is what we're looking at here, but every time it hits something, it's gonna stop in order to turn around. Or from an average point of view, it's just as likely to have a velocity in this direction as that direction. In other words, after hitting, this on average is 0, and that's basically where this is coming from. So that's mv over tau.
Is the reason that we're not using vector signs over the B and the A is that it's going in the direction opposite the field?
Yeah, because I'm hand waving. The force is opposite, so there'd be a negative electric field right there. The velocity is in that direction also. In the end, we really care about just the magnitude of it.
Okay.
That's why I'm leaving it off. Now, ultimately, I'm trying to figure out the current that's flowing here, so I really don't have an individual charge. I've got a whole bunch of charges, and so really, my current is going to be n times the charge of an individual object over the amount of time. And if I look at a section right here, there've been too many mistakes over the years, so that's why I wanted to.
What's the symbol next to N?
Q.
What's
That-
Q?
That? Yeah. Yeah, that's a Q.
Oh, okay.
N is just the number of particles I have. That are the number of those charges that are moving. I'm going to change it slightly here. I'm going to define little n as the charge carrier density. Because what I really care about are the charges that are actually going to flow. I don't care about what all the electrons are. I just need to know the charge carriers. And that's just going to be the number of charge carriers divided by the volume. So if I have some cross-sectional area A of my wire times delta X, that's the volume. So this would just be the number of charge carriers over A delta X. So the number of charge carriers, this capital N there, is just my charge carrier density times the cross-sectional area of the wire times delta X. Questions before I shift boards?
Fox, doesn't it? Hillstown go.
Pardon?
What time is class in?
150. Oh, that clock's slow.
Sorry. I just have work, so that's why I had to ask.
Because Chance has work, we're gonna leave this as a cliffhanger.
Dun, dun, dun.
Anyway,
I'll call in, we can go.
we'll pick it up tomorrow. Have a wonderful afternoon. And Pants, you're back on Wednesday? Okay.
I think, I'll be careful tomorrow. If I can, but if not, so that once the learning, but hopefully I can get on.
Okay. All right, sounds good.
And the master set, sorry, I briefly back to the master set and last,
Okay, I'm fine. Sounds good.
Sorry, not showing the class, I did actually put it later.
Yeah, no, I saw the note.
Oh, okay, thank you. Oh, super.
All right, sounds good.
Thank you.
Yep.
Hey, Dr. Parks, I sent you an email, I just have a fever this morning, that I woke up with, I'm just, not very well.
Okay. I hope you feel better soon.
Yeah, I tested negative still, but if I'm still feeling like crap, I may not show up on Wednesday, because I don't want to expose anyone.
Okay.
But outside of that, I'm still working on all the homework, getting down the proper things.
Okay. All right. Thanks for keeping me in the loop. And hope you feel better soon. Be safe.
Also, I was listening, and I didn't want to interrupt the class, just because I feel like this is a poor medium to communicate. I'd rather just be there and ask questions than just waste everyone else's time by talking to the laptop. So.
Okay. And however you want to work it, you can always send me emails as well. Thank you.
I have a quick question with the, I don't know, number one, yeah, that's slopes. Masters at 25.
Masters at 25? Okay. You said number one?
Yeah, A specific.
All right, so the